Hello, everybody. Welcome to the Atto Fridays. This week's speaker is Dr. Andreas Becker. He is a distinguished professor at the Department of Physics and a fellow of JILA at the University of Colorado, Boulder in the US. So it's very early for him there, and for us it's Friday afternoon. His group works on the theoretical analysis and numerical simulation of ultra-fast phenomena in atoms, molecules, and clusters interacting with intense laser pulses. He received his PhD from the University of Bielefeld, Germany, and worked as a postdoctoral researcher in Quebec City and Sherbrooke in Canada, and as a group leader at the Max Planck Institute for the Physics of Complex Systems based in Germany, before joining the University of Colorado. He's a fellow of the APS and Optica and served as a chair of JILA and currently as co-director of the JILA Physics Frontier Center. And he's going to talk about generation of elliptically polarized high harmonics and attosecond pulses. So the floor is yours. Welcome to the Atto Fridays.
Okay, thank you a lot, Carla, and thanks a lot for the invitation, and good morning or good afternoon or good evening wherever you are in the world. Yeah, it's my pleasure to give you a talk today on the generation of elliptically polarized harmonics and attosecond pulses. I mainly will focus on high harmonic generation. Since I'm not quite sure what is the audience, I would start rather simple, so I apologize for the experts in the audience. I will give you a quick overview of high harmonic generation, kind of things that I feel are important there, how we are looking at it. I will give a short focus during this introduction on a comparison between TDSE and TDDFT calculations. So TDDSE calculation are solutions of the time-dependent Schrödinger equation, while on the other hand, we have the time-dependent density function calculations. And I would like to make a short comparison there. So that will take us a brief moment. Then I will try to lead into the major part of my talk, which will be the generation of elliptically polarized high harmonics in actually a particular setting is cross-polarized bichromatic laser pulses. I will talk a little bit about some historical notes about how circularly and elliptically polarized high harmonics are generated over the last 10 years, because it became a quite hot topic, but then we'll focus on this particular setup of cross-polarized bichromatic laser pulses. Okay, I start relatively simple. So what is high harmonic generation? So we have a laser pulse operating in the infrared or in the ultraviolet with intensities of 10 to the 13, 10 to the 15 watt per centimeter squared. Here is a picture of it. Many photons of starting with an atom or a molecule in the ground state. Many photons are absorbed. We have an electron in the continuum. The electron will be recaptured, and under the recapturing and emission of a higher harmonic of these initial photons will be absorbed. Now, as we will see later, we will have photons that are getting out that can be generated nowadays up to 1 kilo electron volt. So it's a highly nonlinear, non-perturbative quantum process in which we are converting actually photon energy. Now, this is what I like to call the photon picture of it, where we can very easily understand why we are talking about high harmonic generation. Maybe a picture that we are more used to actually is the so-called semi-classical picture, where we are talking about the three-step model, where we are talking in the first step, what was in the last slide, the absorption of photons is a tunneling process here, which is just the limiting process of the multi-photon process. Then the electron is set free. It will be accelerated in the field. It can return, since the field is changing its sign. It will be returned to the residual core here, and with a chance to recombine actually back to the ground state under the emission of light. Now, we will all probably well know that we are generating high harmonics from this, as I explained in the previous slide. This is a typical spectrum of this. It's just a schematic. We have a long plateau. We have a cutoff that can be easily understood here just by this acceleration step. Actually, if we look at it classically, and we get a cutoff up to which we are observing high harmonics actually. Now, if we make a Fourier transform of a part of these harmonics, we are getting an attosecond pulse train or attosecond pulses, depending on in which way we are doing this. So we can have isolated pulses or we can have attosecond pulse trains. I will not talk much about attosecond pulse trains. That's why I keep this here very short, actually. Good. Okay. So what are the theoretical challenges? I'm a theoretician, so I look at this from the theory side on this. What we need to do is, of course, solve the time-dependent Schrödinger equation, which for the hydrogen atom is just the kinetic part, the Coulomb part, and then the interaction with the field. If we have a multi-electron atom, like we often have noble gas atoms like helium, krypton, xenon, or argon, we have many electrons, we have many kinetic terms, we have the interaction of these electrons with the nucleus, we have the interaction of all the electrons among themselves, and we have the interaction of all the electrons with the field. We have several other terms, also the interaction of nucleus with the field, but we can neglect these terms. So these are the main parts in our Hamiltonian. Now, the Schrödinger equation, as we all well know, even for the hydrogen atom in the field, cannot be solved analytically. We have only partial analytical solutions. So either when we have, removing the field here, if we have the electron in the field of the nucleus, we can solve, we have analytical solution, or if we don't have the Coulomb potential, we have the electron in the electromagnetic field. I will come back to this once when we are talking about something that we call the strong field approximation. Now, with this, the question is now, and this is what I would like to talk a bit more detail about this, is we have different ab initio methods actually to solve this time-dependent Schrödinger equation. We can solve time-dependent Schrödinger equation nowadays not only for the hydrogen atom in the field, but also for a two-electron atom. There have been done much progress over the last 1 or 2 decades. For example, the helium atom with a two-electron system can be solved rather nicely nowadays. I would like to focus on 2 ab initio methods that are used very frequently in the field, where we are either solving such a system for the hydrogen atom, or if we want to look into a multi-electron atom, we are solving it numerically by using a so-called atomic single active electron potential, where we have one active electron and we are putting it into a potential where all the other electrons are frozen, as well as the nucleus. Now, this is something that many groups in the world nowadays can do. On the other hand, we see also some activity in that people are using time-dependent density function theory, for example, because we can solve it with all the terms here in a special way, to see, for example, if electron-electron correlations are playing a role in certain calculations. Now, I would like to spend a little bit of time on comparing these 2 methods, actually, because there is sometimes the question, actually, if time-dependent density function theory can give us accurate numerical results, actually, that we can trust, and how much we can actually understand from this, whether electron correlation effects are playing a role. Now, from my point of view, and what we have done in my group, was that we ask ourselves the question, can we have a strategy where we are comparing calculations that are done with a single active electron potential and the time-dependent density function theory. And the question was then, can we maybe validate with this the accuracy of time-dependent density function calculations, and on the other hand, also of the single active electron potentials that we are using. Now, here's the approach that we have taken there. So what we have done is we have computed an effective potential using the density function theory. You're doing this for different orbitals. These are the so-called Cohen-Sharma equations. I will not go into the detail of this. If you're not familiar with this, just consider you get an effective potential for each of the shells out of this. That has a form of this, that you have a long-range part, you have electron-electron correlations, and you have a so-called exchange correlation interaction. Now we are taking this potential and doing then 2 things with it. On the one side, we are propagating the orbitals just with time-dependent density function theory. So we are doing a full density function theory calculation. Actually, this is done in collaboration with Agnieszka Jaron and her group, who are expert in these kind of calculations in the meantime. On the other hand, what we are also then doing is we are taking this effective potential that we are getting from density function theory and fitting it to an effective single active electron potential. We are taking an analytical form with a long-range potential, with a short-range part, and with a part for each shell that we have here, actually. I will show you calculations for the helium atom where you have only one shell, but you can do this also for the argon atom. You can do it for a krypton atom. With this, you would have many more potential terms here. Now, with this, we are getting a single active electron potential based on the potential that we get from the DFT here. We perform then an ab initio single active electron calculation. And then we want to compare results here, actually. And what we are doing here, I'm showing you today some results for high harmonic generation vector, because this is what my talk is about. And we believe also this might be, especially if we were expecting, if we are looking towards the cutoff, electron correlation effect should not play so much of a role. So we would expect actually that we find agreement between the two of them. Now here I show you results actually for the helium atom. It's not actually exactly the helium atom because the ionization potential is not quite right. It was off by about 10%, but it's a 2-electron system at least. And we are doing time-dependent, as I showed you, time-dependent density functions calculation and TDSE calculation. The TDSE calculations are the black solid line. The TDDFT calculation is the red dashed line, actually. And what you see here is that in most of the spectra, actually, you can hardly distinguish actually the two lines with each other. So we found actually, and we were very amazed by this, that we find a remarkable agreement between these two very independent calculations, actually. So this, we believe, gives us the ground, first of all, that we validate that one can do time-dependent density function theory calculations and that they will be accurate. And if we find this kind of basis, then from here we can go on and actually look really into electron correlation. Now, as you see, there are small differences here. They are not so small because, as you see here, there is a logarithmic scale, actually. So that might be actually a factor of 2 here already. But overall, I think it's a remarkable agreement, especially if you look here at 600 nanometer. Now, the convergence was difficult to reach between the two calculations. Actually, that's why we went only up to 600 nanometers and up to 4 cycles, cycle laser pulses. But still, I think we can build this ground actually where we can trust both of these calculations and can make comparison actually between them. And maybe the strategy that I showed you on the last slide is actually a way how to do this. Okay, I would like to go on and quickly just mention an approximation that I believe everyone probably in the audience is aware of, and I will not use it in my talk, but I will mention it at some point. That's why I want to quickly introduce it here also. That's the so-called strong field approximation. It's an approximation method in which we are taking with, in different steps actually, here, I'm showing it here again for the high harmonic generation process, where we are showing in different steps, actually, we are not taking the full solution, not the full Hamiltonian, but we are approximated, actually. In the initial step, actually, the electron is bound in the field. So we are taking just the kinetic term and the single active electron potential in this approximation. In the intermediate step, where the electron is set free in the field, we are taking the kinetic energy and the field interaction. And then in the final step, when we have recombined the electron, we will be back in the atom. So we have the kinetic energy and the single active electron potential. Now you can find and coming back to this, you have, remember probably that we can find solution from here. We can find solutions from here. Actually, these are the similar ones. And we have also an analytic solution for this part. So we can build up a so-called S-matrix theory and S-matrix expansion, and we can do calculations there. There are different ways actually how to do these calculations. There is something that is called saddle point approximation or stationary phase approximation. People have done this in many different ways, but this is the kind of key that is behind this approximation, which is extremely successful in our field and has helped us a lot in understanding different processes. And I believe here, for example, for this process of high harmonic generation, it's very well fitted. I will not use it, but I will mention it later again so that you just know what I'm talking about. Okay, now I'm talking today only about the microscopic part of high harmonic generation. That is the part that you see down here. This is the three-step process that I've just told you before. We have an ionization step, we have an acceleration step, electron wave packet is coming back, and we have a recombination step. Now that's the microscopic or single atom part of high harmonic generation, and that's everything what I will talk about today. Now there is a second part to high harmonic generation that one needs actually to understand, especially if one analyzes in detail experimental results, and that's the so-called macroscopic part, because we have not just one atom in our laser field, but we have many atoms. Each of these atoms or many of these atoms are radiating, so we must phase match actually the radiation that is we are getting from each of these atoms. There is a lot of work done on this. Even people are working on combining solutions of the time-dependent Schrödinger equation to describe this part of the process, and the Maxwell equations to describe the macroscopic part. So there is a lot of progress done. There's also approximation methods. My group has also worked on this. I will not talk about the microscopic part today at all, but I just want to mention it. Now we are very successful actually in our field actually in describing the high harmonic generation process. And I give you just one example, and of course I give you an example I was involved with, which I think shows how well we can describe nowadays this process in certain cases actually. What you see on the top is an experimental result out of the group of Margaret Murnane and Henry Captain here at JILA, who has driven this high harmonic generation process quite a bit. And especially they were the first ones who had generated 1 kilo electron volts higher energy photons with a mid-infrared laser field. And if you think about this, how you are making out of mid-infrared photons, 1 kV photons, you must combine more than 5,000 of this process. Now you understand probably why this is really a highly nonlinear process actually. Now the spectrum that they see is this spectrum here for the driving laser pulse of 3.9 micrometer. And here's a calculation that was performed by Carlos Hernandez Garcia when he was here in JILA with us. And you see this combines actually the microscopic and the macroscopic part of the process. And you see actually this is a linear scale here, what you see. The overall shape of the spectra are fitting very well with each other. Having in mind that this is such a highly nonlinear process, I think I'm still amazed about this kind of comparison that was found at that time, actually. Now, here at JILA, and let me talk for a moment about JILA and what we have done here. There were several experimental milestones and theoretical predictions, actually, that were done in this field, and all this was mainly driven by the group of Margaret Murnane and Henry Captain on the experimental side. I've shown you that they were able to generate kilo electron X-ray harmonics. I will talk a bit about different ways because it leads me to the main part of my talk, how they have generated circularly polarized harmonics. They have generated high harmonic generation in multiply ionized plasma. I will not talk about this. Theoretically, we have looked with them together at how we can generate maybe not just attosecond pulses, but zeptosecond pulses, and maybe how one can make isolated circularly polarized attosecond pulses. So as I said, most of this has been driven from the experimental side, and I want to talk for a moment about now these different ways how to provide circularly polarized harmonics. Now, everything what I've shown you so far was actually high harmonic generation with a linearly polarized field. And if you put a linearly polarized field, if you put a wave packet into a linearly polarized field, so here you have this wave packet, then Carlos Hernandez Garcia has done a nice movie of this one. So if you drive it, you see that the wave packet is actually sloshing back and forth. So you see ionization, but you see also how the wave packet is coming back. It is getting more and more disturbed, actually. And this kind of disturbance is leading to high harmonic generation, actually. Now you see clearly that there is an interaction of the wave packet when it's leaving with the core that is remaining, actually. Yeah. Now, what you're generating out of this one is, since you're driving the electron back and forth along a line, you would generate also linearly polarized harmonics. So the question is now, how can I get harmonics that are not linearly polarized, but circularly polarized? Now, the simplest thing to think about this is, well, instead of putting it into a linearly polarized laser field, I put it into a circularly polarized laser field. But you can quickly, convince yourself that that will not work, because if you do it and you drive it and you wait for a moment here, now how the wave packet is evolving, you see that it's actually circling around the core and it will never return to the core, actually. Now that was predicted a long time ago already, but here you see it very nicely actually in the animation that Carlos has done. So you cannot just put an atom in a circularly polarized field to get circularly polarized harmonics. So you will not generate any harmonics with a circularly polarized laser pulse. You need more than one circularly polarized laser pulse. And that was realized the first time in 1995, when there was the first proposal how one can make circularly polarized laser pulses. This whole thing was picked up quite a bit again, and different kind of methods were developed around 2015, 2016. Since then, this whole methods of producing circularly and elliptically polarized laser pulses has evolved quite a bit. Now, here are two methods that have been studied here at JILA actually quite a bit. And the one is where it's taken collinear circularly polarized pulses, one that is left-handed circularly polarized, the other one that is right-handed circularly polarized. And with this, you can figure out that you actually get circularly polarized high harmonics. Now, I will not go further into this one, but I want to talk for a moment about the second one here, actually, because I want to show you I want to discuss one of the two methods actually a bit more in detail. In this one, it is actually here why you are taking two color fields. So probably, for example, an 800 nanometer field and a 400 nanometer field. Here you're taking two 800 nanometer fields, one right-handed polarized, the other one left-handed polarized, but this time they are not collinear propagating, but they are propagating at an angle and interacting then with the gas. Now, how do you get now circularly polarized harmonics out of this? You can think about this in two different ways. The one wave is that you are adding up just wave vectors from the photons of the two different fields. Now, for example, here we are taking 4 photons of this polarized field and 3 photons of the other polarized field. And what you are getting up with is, if you are adding all this up, you will come out with one large photon, a 7th harmonic here actually, that is polarized in the same way like this field. You can do the same thing in the other way around, and you see that with opposite polarization, you will find a photon on the other side. Now, this is a very nice method actually to separate right-handed and left-handed polarized photons spatially. You can think about this in another way also about this process. So this picture tells you very nicely how you are separating the photons, how you are generating them, and how you are separating left-handed and right-handed polarized photons, actually, which is nice to do it experimentally in a separate way. Okay. A different way how to look at this is actually if you combine these two fields, at the target atom and you're looking into a plane that is transverse to the propagation direction of these two fields here, you will find out if you do this, that at each point along this transverse position actually here, what you will get is a linearly polarized field. So there its two fields are adding up and providing at each point a linearly polarized field. But if you're moving from one point to the next point, the direction of your linear polarization is changing actually. So you have here an atom that is generated linearly polarized high harmonics along this direction, while the next one is doing it in this direction, and so on and so on. And in the far field, all these things are adding up together and you get a circularly polarized field. Now, the interesting part is still that microscopically, you're dealing actually for each single atom with a linearly polarized field. And you have a high harmonic process that we understood for many, many times. And out of this, for example, we know also techniques how out of these high harmonics, we should be able to isolate how to create attosecond pulses and actually how to isolate these pulses. So let me very quickly go over this and show you that how you can do this is either if you take a long driving pulse, we know that we create an attosecond pulse train. So it will be a circularly polarized attosecond pulse train from each of these interactions that we have in the long pulses from each of the cycles. But if we make a very short pulse, we will get an isolated attosecond pulse. Just in the same way, like we have done it, we have learned it for linearly polarized pulses. And why does this work? Because the interaction at each position in the plane is actually an interaction with a linearly polarized field. The other way that you can do this is actually you're time delaying the two pulses, so that are coming at a non-collinear angle. And what you will find is that if you start to time delay them, then at the beginning you have just a circularly polarized pulse. Then when the two pulses overlap, you will have it linearly polarized. Then you will have it again only circularly polarized. So you're actually restricting here the interaction time of the two pulses with each other. And again, if you go from zero over from full overlay to some time delay, you are shortening the pulse and you're going from an attosecond pulse train to a single attosecond pulse and to an isolated attosecond pulse train. The same methods actually that we have learned before already for linearly polarized pulses. Now, this was predicted first theoretically and then later was shown experimentally, and shown experimentally not only that you can generate isolated attosecond pulses with this time delay process actually, not only circularly polarized pulses, but if instead you're taking these non-collinear pulses not to be circular, but elliptically polarized, then you can create even elliptically polarized attosecond pulses. Now, and this leads me now to the main part of my talk, that this introduction towards circularly and elliptically polarized high harmonics. Maybe I would like to talk with you about one other simple setup actually. How can you generalize elliptically polarized harmonics? And there was a little bit of discrepancy actually between experiment and theory, and that's why we became interested in this. Now, it is a simple setup actually that we are talking about here, because we are talking about two laser pulses. Both of them are linearly polarized. Let's say one is at omega, let's say it's an 800 nanometer pulse, and then we have a 2 omega pulse, which is a 400 nanometer pulse. Both of them are co-propagating, but as you see already, I'm calling them cross-polarized, because one is polarized, let's say, in the x direction, and the other one is polarized in the y direction. Now you're overlapping both pulses with each other, and you are performing an experiment with this, and you're looking for high harmonic generation. And this was done in 2015, this experiment, and it was reported that one sees out of this experiment actually harmonics that are at least partially elliptically polarized. Now you see here they found results for odd harmonics, and they found results for so-called even harmonics. The harmonic order is here given in multiples of this omega field. That's why we have odd harmonics as well as even harmonics. If you want to see the overlap of the two fields, it's shown here. This is once again the omega and the two omega field. Now they are stating already in this abstract that this is a simple technique, and yeah, this seems to be experimentally and simple to read. They reach high degrees of ellipticity. So let's quickly summarize what they really observe here. Now they are showing us harmonic orders that are relatively large actually in this experiment, and actually they are reporting these large ellipticities for harmonics near the cutoff, actually, around the cutoff. They are not talking, as far as I remember, much about harmonics in the plateau. So they are focusing on this part. They say also that the ellipticities are large for even harmonics, as you can see here, but they are much smaller for the odd harmonics, actually. And then maybe what is interesting for the parameters that they have used in the field, in this experiment, I think if I remember it correctly, it was an experiment on argon. The intensities of the two fields was 1 to 10 with the 800 nanometer field. Harmonic orders is given in the multiples of the 800 nanometer fields is 10 times stronger than the 400 nanometer fields. And they reported that actually their pulses do not fully overlap, but they needed a certain time delay. And you see here two different lines here, a solid line and a dashed line. This means just that they have taken two different runs, but for both of them, these kind of general statements are correct. So far, so good. Now, that at that point was a bit of a surprise, actually, because there were predictions before that with this kind of setup, you should not be able to observe any kind of harmonics. And these kind of theoretical predictions were done with the help of the strong field approximation. And as really, you might want to remember this already, it was done in the so-called long pulse limit. So where we have very long pulses actually, because, for example, this saddle point approximation was being done. And it was shown in this and argued in this, and this is not just in this paper, but in several other papers, that you should not get out of this ellipticity at all. Because what are you doing is that if you're putting this down in harmonic orders in this driving fields omega, you should produce odd harmonics only due to the interaction with the omega field that are actually polarized parallel to the polarization direction of this driving field, which means they are linearly polarized. On the other hand, the even harmonics in the multiples of omega here, you should only find that they are polarized parallel to the two omega field. So there seems to be a contradiction here between experiment and theory. Maybe, maybe not, we will see. Okay, so we became interested in this, that there seemed to be something that needs to be resolved. Okay, so let's have a look, and we were not the only one who became interested in this. So let's look a little bit into, we have a lot of different parameters here that we can play with actually. First of all, we have two fields, and we can play with we can change the driver laser intensities. It was in the experiment, it was 1 to 10, but we can also think about 1 to 1, 1 to 2, etc., etc. So we can change in theory as well as in experiment this relatively quickly. Now, I told you also already about this. We can talk about the interaction time. Namely, we can change the pulse duration of these two pulses, or we could even time delay them, and we have the joint interaction time we can control with this. And then there is certainly something also like the carrier envelope phase of a pulse, and let's talk about the relative carrier envelope phase, how the carrier envelope phase of one pulse is related to the other, to one of the other pulses. We can do even more. We don't have to think only about omega and 2 omega. We could think about a setup that is omega and 3 omega. We could think about that these pulses are not exactly orthogonal polarized, but they are polarized, still linearly polarized, but at a certain angle also. Or we could say, okay, they are maybe not completely linearly polarized, but there is some ellipticity actually into this. Now, all these things have been studied quite a bit, and I named just a few people here, and I'm missing a lot, I know. So, but maybe these are some of the major actors who have worked on this. We have not done all this. So we wanted to stay as close as possible to the experiment. So we have not considered all these parts. We have not changed the driver laser wavelengths. We are exactly orthogonal polarized, and we take exactly linearly polarized pulses. We stayed with the driver laser intensity at 1 to 10. We didn't consider time delay, but we changed pulse duration as I will show. Okay, so what are the numerical results here actually? So here are the numerical results that we get out of a single active electron time-dependent density, time-dependent Schrödinger equation. Now for hydrogen, of course, it's a single active electron calculation. There is only one electron. What I'm showing you here is now the spectra. We have broken up the spectra into two components, namely the two component of the spectrum in the x direction and the one in the y direction. And you see here the part that is in the x direction, and that here is the part in the y direction. If you want to have the complete spectra, you would have to add the whole thing up. And what you see down here is the ellipticity of each of these harmonics actually that is generated. Now you see very clearly that due to the omega field, we are getting all the odd harmonics here. And then you see a kind of unstructured, what we often have, where the harmonic orders maybe are not so clear, but then at the cutoff, they become very clear here again, and we are exactly at the odd harmonics actually here. While if you look in the y direction, which is the 2 omega field polarized in, we see from there actually really the odd harmonics here. And once again, very clearly again at the cutoff and here in the first part. Now looking at the ellipticity, we see most of the time actually an ellipticity that is actually 0. But then here in the cutoff region, we see very clearly that there is something going up and down. And if you look carefully, we see large ellipticity actually for the even harmonics, while we see almost no ellipticity for the odd harmonics, exactly what has been reported also in the experiment. Now we wanted to check this. We have done several runs for hydrogen certainly, but we wanted to check it also not only for hydrogen atom, but also for the argon atom. So we did another calculation for argon, same parameters exactly, which works nicely because they have almost the same ionization potential. Again, you see odd harmonics in the x direction and even harmonics in the coming in the y direction. And here you see even more clearly that we have this change of almost no ellipticity in the odd harmonics and large ellipticity in the even harmonics. And this whole thing comes mainly out here in the cutoff region. So that's why we went, after we have confirmed that we get something similar out like in the experiment, we wanted to understand this further. So we looked at the ellipticity of the harmonics, and actually there are different ways how to define ellipticity. We went with a definition that was developed by Owen Cohen in his group actually, where ellipticity is defined in this form. And if you look here at the argument, then we have two parameters in this one. One is the signal intensity ratio, namely the signal in the y direction over the signal in the x direction. Now you understand probably already why I have shown you both of these parts actually in the spectra. And the signal phase, actually, we have a phase of the signal in the x direction, and we will have a phase of the harmonic in the y direction, actually. And it depends in this form. Now you want to have a high ellipticity, and if you plot this function here now as a function of this argument here, you will see that you get high ellipticity if this argument either becomes 1 or -1. You see this at the end. What does this mean? When do we get actually these high ellipticities? Well, we need a phase difference of this. We want to have the sign is equal to 1 because we want to have this whole argument equal to 1. So we want to have sign equal to 1, which means we need a phase difference of pi12. And if you can convince yourself what we want to have as a signal intensity ratio, actually, we want to have this signal intensity ratio also equal to, we want to have it equal to 1. Now, that's not surprising. You could have convinced yourself immediately if you're overlapping two different fields, you want to have that the fields are equally strong and that they have a phase difference of pi12 to generate actually circularly polarized parts. You might have learned this from your E&M class. Actually, I'm teaching at the moment E&M, and my students are working on this in the homework. So they figure exactly something like this out. So let's keep this in mind. We want to have a single intensity ratio of 1. And this is the first thing that I will focus on here. Now, if we are going back to this result in hydrogen here, and we are looking at the odd harmonics in the cutoff region, we see that the signal difference between the x direction and the y direction is for the odd harmonics actually relatively large, which means that the ratio is 0, and that's why we have an ellipticity that is actually small. Now, if we are switching to the even harmonics, we see that we have actually a signal intensity ratio. The two signals are becoming much closer to each other, and that's why we have a signal intensity ratio that is significantly larger than 0. And we see that we have, due to this, actually higher ellipticity. And we see even that as closer the two signals are coming together, as higher is the ellipticity, exactly what we were expecting. You can go through the same thing in argon. Actually, here again at odd harmonics, you have a large difference between the signals in the two different directions. Ellipticity 0. Once again, here, if they are close to each other, you have a higher ellipticity actually. Now, one thing that is pretty clear is that these signal intensities we can control just with the driving laser intensity. Now, we have calculated everything for the ratio of 1 to 10, as I told you. If I make it to 1 to 2 or 1 to 20, I will shift relatively the strengths of these two curves, and I should be able to control here actually whether I see high ellipticity or low intensity. I still see, as long as I keep the 400 nanometer field, the 2 omega field, in intensity lower than the 800 nanometer field, I will always have higher ellipticity for the even harmonics than for the odd harmonics. That is one way how to do this, and I believe I don't have to show you results for this because that is relatively straightforward. But there's a second way how to do this, and the second way is to do it with the pulse duration, actually. So for everything what I show you here now is, I would keep the laser intensity, actually this ratio the same. So I would keep this 1 to 10 ratio, and everything what I show you at the moment is for hydrogen atom. Now, if I'm changing now the pulse duration, we see the following. Now, we know very well that if you have a very short driving pulse duration, we will get a very unstructured spectrum, actually. We will not get clear harmonics. This is very well known. And here's a calculation, actually, that we have done for 7 cycles, and I'm concentrating now only on a small part of this, of our spectrum. And you see there's large differences everywhere between the two signals. And I would expect we would maybe get small ellipticity only out of this. On the other hand, if we are now making pulses longer and longer, we know that we get sharper harmonic lines, actually. And this is what is shown here now. We are getting sharper harmonic lines from the X driving laser field in the X direction. So we are seeing here the odd harmonics developing. And on the other hand, we have also the even harmonics developing. But you see what is happening, actually, this part is raising while this value is decreasing. And we are starting to match now for the odd harmonics the two signals. If we make the whole thing even longer, well, this harmonics will become more pronounced, and now this off harmonic part will become smaller. The even harmonic part from the y direction will become larger, and we don't have such a good signal intensity matching anymore. Now, we cannot go in numerical calculations to infinitely long pulses, but we can easily understand this, that these lines will become sharper and sharper. And that's why we will come to something that is where the signal intensity ratio will become very unfavorable for the odd harmonics, but also for the even harmonics. And remember, that is the part that was predicted by the SFA in the early theoretical prediction. So what we should expect for ellipticity is now small ellipticity here for the 24th harmonic, best ellipticity or highest ellipticity for an intermediate pulse duration, and then again, smaller ellipticity if we are making the pulse duration longer, and then it should fall off, actually. So this kind of calculations we have performed, and we see exactly this result. So here is the ellipticity of the 24th harmonic shown as a function of the duration of the 800 nanometer field. So we went from 5 cycles to 40 cycles, and you clearly see that there is an optimal pulse duration in agreement with the picture that I've just tried to explain you, where we're seeing the highest ellipticity that are actually reaching a rather high point. And we see that ellipticity falls off quickly as the pulse duration increases, becomes longer and longer. And in the very long pulse limit, we should actually expect that the ellipticity becomes 0. So in this sense, there is actually no contradiction between the experimental results and the previous theoretical results. Only we have to understand that there is an optimal pulse duration. And this optimal pulse duration you can certainly get by varying the pulse duration, or you can shift the pulses with respect to each other. So you're either talking about an optimal pulse duration or an optimal pulse delay. And the pulse delay is that what is done in the experiment. Now, the last 5 minutes or so, I would like to go one step further. First of all, I would like to show you this is not only true for hydrogen, but it's also true for argon. We just find that the optimal pulse duration for argon for the parameters that we have chosen is not 20 cycles, but it's just 10 cycles. So this optimal pulse duration depends actually on the laser intensity ratio, and it depends on the target atom. But again, here we see the same result. There's an optimal pulse duration for very long pulse durations. The whole thing goes again to 0 as it was predicted before. Now, I would like to take this one step further, because after we have done this first calculations, we did a more refined calculation, and the thing became a little bit more complex, actually. So here's the refined calculation for the ellipticity of the 24th harmonic, actually. The points that I've shown you before are these blue squares, actually. But then we did more calculations, and actually we saw not a continuous line that went like this, but we saw an absolute oscillation that went up and down. Now, somehow before we were a little bit lucky, because we somehow got always we were near the maximum, and we had this nice continuous curve, but now we have an oscillation curve, actually. Yeah. So where is this oscillation coming from? And now let's go back to the ellipticity. And so far, I've talked with you only about the signal ratio here, the signal intensity ratio here. But there is a second factor in this one, and that is the phase difference, actually, that so far we have kept fixed. But if you see an oscillation, and I see a signed term here, then immediately one gets, of course, the idea that this must come from the signal phase difference here. So I will focus now into one part of this here, and we'll look with you together into the signal phase difference. So we can look at this difference in the harmonic phase difference, and that is what is plotted here from minus pi to pi are the results. We are looking only in this part between 15 cycles and 25 cycles. That's what is shown here, between 15 and 25 cycles. And we are looking at the 24th harmonic, and we are looking at the 25th harmonic. And you clearly see that this phase difference is actually changing rapidly over this as a function of pulse duration, which explains immediately this kind of oscillation. You can even see here for the 24th harmonic, we have at 15 cycles, we have a phase difference of about pi half. That's why we have a maximum here. At 25, we are again at pi half. That's why we have a maximum here. And here we are at minus pi half. That's why we have a maximum here. And we were just lucky to get always the maxima, because in between, you have other results. Actually, with sign, you have a phase difference of 0, etc. So we got a bit more interested in, this is a phase difference here now. So there is a phase of the harmonic in the y direction and the phase of the harmonic in the x direction. So we thought, okay, are both of them are varying, or only one of them is varying? So we looked in now not only in the phase difference, as a function of pulse duration for these two harmonics, but we looked separately into these two. Okay, so what you see here is once again the picture that I've just shown you on the last slide. And here you see the x part of it, so phi of the contribution in the x direction, the phase of that one. And here, the part that comes from the y direction. And you see, here's a strong variation that we see here, but on the other hand, we see for the 24th harmonic, while for the 25th harmonic, we see something very constant, actually. And for the y direction, it is actually exactly the opposite. We see a large variation for the 25th harmonic, but at the 25th harmonic, but a very small variation only, or almost constant one, at the 24th harmonic. So if you think about this once again, then we see almost no phase variation for the harmonic itself, because the y part creates is the main part where we have on harmonics for the even harmonics here, but we see a large variation within this off harmonic radiation. The same thing for the x direction, where we see almost no phase variation for the odd harmonic here in the x direction, but while we are at the off harmonic radiation, we see a lot of variation actually. My last part on this one is only that we are investigating this at the moment further. The question is now how you can control the signal phase difference. And you can control it, as you see here, very nicely, actually, if you're controlling the so-called relatively carrier envelope phase. So the carrier envelope phase of one pulse as compared to the other parts. If you vary this carrier envelope phase, you see a clear variation of the signal phase difference. Signal phase difference, actually. And there's a one-to-one correspondence, actually, to the variation that you then see in the ellipticity of all the harmonics, actually, that you have. So this is clearly this part of the oscillation that we see as a function of pulse duration is coming from the signal phase difference and is reflected in the ellipticity of the harmonics, actually. Okay, with this, I believe my time is more than up, actually. I spent probably a bit too much time. So let me just quickly summarize. What I've tried to show you here is actually that we could confirm the experimental results that one can find large ellipticities of high harmonics at the cutoff. We can control it via the ratio of laser intensities. More importantly, actually with the help of pulse durations or the time delay between pulses and the carrier envelope phase. So I fully acknowledge something that we have not investigated up to now. There are a lot of other parameters with which I can also create large ellipticity of high harmonics at the cutoff. I could not show you any results because we have not worked on this up to now, but there are clearly wonderful results out in the literature. So let me finish up by telling you about my team and mentioning that Bijan Gomashi, who is a PhD student in my group, was the main contributor actually to this work that I've shown you today, together with a previous PhD student who is now at Ohio State University, Spencer Walker. And there are a number of other people, especially I'm very happy to work with Margaret and with Henry, who have taught us a lot about high harmonic generation on the microscopic, but especially also on the macroscopic regime. So thank you very much for your attention.
Thank you so much for your talk. Other questions, comments? Wilhelm. Yes, go ahead. You can mute yourself, you're fine.
Okay. Can you hear me now?
Yes, we can. Okay,
great. I mean, thanks for a great talk. I mean, that's very interesting. And my question is the following. Dejan Milosevic and I and Dino Habibovic, we ran SFA calculations for the same situation, cross-polarized omega to omega fields. And of course, we got the result that you expect in the SFA, linear polarized harmonics in one or the other direction. Okay, so far so good. But so we had this contradiction with the experimental results of Lambert et al. But when we ever so slightly change the geometry by introducing a tiny deviation from orthogonality or tiny amount of elliptical polarization of the incident field, then we obtained significant elliptical polarization for the harmonics. And this is, we couldn't find the physical reason of why this would happen. But the point is, if these results were true, then basically that would rule out any meaningful comparison between experiment and theory. So my question to you is, did you also consider slight deviations from the ideal situation of cross-polarized incident fields?
Yes, thanks, Willem, very for the question. Very interesting thing, and actually, I'm very much aware of the calculations that you have done. I have two comments on that. To your real question, or the question that you asked me, did we consider this? No, we have not done so far, but that is certainly on our agenda, because that is a very interesting point that you have made there, that you had to change this by a slightly bit and you suddenly saw a very different result. Yes, I've noticed that you had some interpretation of this, but it seemed that you were not completely satisfied with this. So it is on our agenda to look at this. We have not done so far. I would like to make another comment. We have done also SFA calculations, and we have done SFA calculations without the saddle point approximation or the stationary phase approximation. So we did the integral actually that you have to perform fully. And we see very similar results between numerical results and SFA results, actually. We clearly see that there is an optimal pulse duration also. We are still working on that, so to make sure that we have done everything right. But I believe one can do it, or at the moment it looks like this, that one can get similar results also with SFA under certain conditions. To answer your question, no, we have not done it, but it is something that would be very interesting. We were very interested to do actually in the future.
Yeah, thank you.
So are there further questions, comments? So I don't see any, but you mentioned that you did a calculation without using the saddle point. I would imagine that things then are not as black and white as when you have a saddle point, that you have a width and that you have some blurring, and this may make a difference in your case.
That's right, and that's why we want to be very careful before we are actually publishing it. But we are aware of this, that there is this discrepancy with SFA, and that's why we wanted to look into this if we cannot resolve that part also. Yeah, but I cannot tell you more than initial results showed that we might be able to find an agreement there, actually, at least qualitatively. You can never expect that you have full quantitative agreement. But
I agree.
That there is an optimal pulse duration, this seems to be the case. Yeah.
Mm-hmm. I know, because there's some work from Manfred Lein's group, I think, with Camilo Ruiz, where they looked at molecules, and like all the phase jumps that they had without using the saddle point approximation were much more smooth and blurred. So I expect it would be the same.
Yeah, that's possible, yeah.
Yes. Any further questions, people? No, I see a lot of people around today, but people are quiet. It's Friday, as I said. But, I mean, if not, thank you once more. We're going to give you the chance to talk to the speaker in a more private setting, because currently we are on YouTube as well, and we have quite a few people joining online from the YouTube channel. So for those who are watching on YouTube, have a great weekend. Thank you for joining. Hope to see you in 2 weeks, and thank you also for supporting the speaker. So take good care of yourselves, and we're going to finish the streaming right now. We have one in Q&A from Anonymous. Interesting talk. I was wondering why the ellipticity and distinct harmonics were observed only after the cutoff and before the thresholds.
Yeah, you can see this a bit in this last slide that I show you here. So if you look at the comparison of the signal phase difference as a function of this carrier envelope phase difference, then you see a very clear picture here for the highest harmonics, and actually the cutoff is here around 20 or 22, I believe. And you see also this clear picture in the ellipticity of the harmonics. But you start to see a very blurred picture actually here if you if you go into the plateau, and it becomes even more blurred and not so nicely structured anymore if you go to lower and lower harmonics. And you see the same thing is happening here actually in the ellipticity of the harmonics. It seems that it comes somehow from this. So let me leave it there. I don't have a full answer there. Yeah, but that's an indication actually.
Okay, so thank you all so much for joining. Are there further questions? I had almost missed this one, but I hope it's okay. Let me know if you would like to ask further. So we're finishing the streaming. We'll be back in 2 weeks. For those on YouTube, have a great weekend and hope to see you soon. I think it's okay with the question, yes. And take good care of yourselves, and I'll see you in 2 weeks. We're getting questions now, but anyway, we're stopping the streaming. The other question is, hi, this is Juan del Valle. How reliable is the SAS single active electron approximation when describing argon? In terms of energy levels, the single active electron approximation provides usually bad results. What about other relevant quantities?
Yeah, we have tested it actually. I showed you at the beginning this comparison with TDDFT and TDSE. We have done it only for helium so far. I would expect that for argon, it might be worse. And especially the one who is asking the question is completely right. If you want to do there a clear comparison with experiment where the excited states are playing a role, you will have a hard time to do this with a single active electron approximation. Yeah, you have to be very careful. I completely agree.
Okay, so you can also speak if you wish and pursue your question further. No? But it's a good point. I mean, there are giant resonances in other species as well. Thank you. Okay. So we're finishing this streaming. I said that 3 times already, but I'm very happy that we had some questions in the end and that people raised their hands or typed in the Q&A. So people from YouTube, take good care of yourselves and hope to see you in 2 weeks.